Welcome back, computer touchers, professional keyboard enthusiasts, part-time programmers. We're back once again. This is day 13, 14, 15. I can't even tell anymore, to be honest. I literally cannot tell anymore. I only know once I upload the video. But might do a bit of a longer session today. But before that, maybe some reflections. I took a test. Yeah, I took a test for just a coding test of sorts by a prominent cloud entity. And I got fried. I'm gonna be honest. It was two parts. The first part, you have like 100 minutes to do it. Part one, I'm in there like, oh yeah, problem number 44 plus problem number 62 minus problem number 12. And, I'm getting in there. And the problem is actually not that hard. Actually the difference is on LeetCode, you're doing a problem, they're getting right to the meats and potatoes. They're like, this is a string, this is an array, do the thing to the string in the array. In the coding test I was taking, there was an absolutely elaborate story with character arcs and rising and falling action and backstory and lore. And it's like 8 paragraphs, and all they really want you to do is to do some string and number manipulation, but you really gotta like Sherlock Holmes through the text to like figure out what you're supposed to do. I guess the point of that maybe is for it to mimic real life, because when you're working on something, I guess, it's supposed to be like, when you're working on something, maybe it's supposed to be like, that's how it is. You work with someone, your boss gives you some work or something, or your lead, and you gotta work with them, and like, it's not that black and white with like, on LeetCode, you get your exact problem constraints and the exact edge cases, and the tests are already written. So I get it. But still, I was a bit thrown off by that. I might even say that I didn't like it. That was weird. Having to read that many paragraphs just to figure out what the problem was, I guess that's the real life programming. Anyway, I got fried. I fried the first part, string and array manipulation, basic stuff. Not really, actually. The stuff that I do, most of the problems that I've done so far, like string and array, so I'm feeling pretty comfortable there. So that part wasn't too bad. Also, you have to read really closely. I technically fried this problem in like 15 minutes, but I spent extra 10 to 15 minutes debugging something that was like non-existent. Basically, there was some general phrasing. It was like, oh, the output should be sorted in ascending order. And I guess you're supposed to figure out exactly what part of the output should be sorted in ascending order. And there were 2 options. And I just assumed like, the one that made the most sense. In real life, it would be sorted by the one I chose. But I guess that's kind of how to get you with these problems. It was sorted by the non-obvious one. And so they got me there. So I spent another 15 minutes, and the solution ended up just being that I had to sort by a different parameter. So I literally just changed like 3 letters, and it worked. The second one, I spent like an hour thinking on that one, and then I realized actually that that my brain was actually fried. So I worked all day, and then I do my problems and whatnot, and then the assessment was 2 hours long. And if I did a whole bunch of stuff before, actually my brain was fried for the second problem. Even going into the first problem, I could sense that my brain was fried. So maybe there's some, recovery logic, some recovery rest. We're kind of like mental athletes a little bit. Maybe there's some recovery process we have to do before the problems. That being said, we're locking in a 2-hour session today. No recovery. Okay, I'm going to try. I usually do 20 minutes to 40 minutes. I'm going to try for an hour. It's mainly because I have another 7 days to do another assessment because that first one was a demo, and this one I have 7 days to do is the actual one. But I'd like to nut up before that moment, so I feel like I got to turn the burners on. But at the same time, I turn the burners on in terms of effort, in terms of these problems. I also got to turn the burners on in respect. Actually, I should have a bigger camera when I'm going to talk so much. I'm just going to make this big. I should have a bigger, okay, this is too big actually, I'm uncomfortable. At the same time, I have to also think I have to turn the burners up on the level of recovery that I'm doing, or maybe we're all doing that, you know, before you actually try something. I didn't realize that. Even on some of the problems recently that I've been doing on daily, I've noticed that sometimes when I pull up to actually do the problems daily, I'm actually tired. So I don't know if I'm working my mind too hard. I guess that is what that means, maybe. Or maybe I'm not. I think I'm working my mind enough. I'm just not doing enough rest, I think. Like after I'll finish my problems or something, I'll just like go and zonk in on like YouTube or something for an inordinate amount of hours. I don't usually watch YouTube. At least not that much recently. But recently, I removed my screen time, which lets you like limit your like YouTube time or whatever. So I've just been going crazy. I've just been zonked in. So yesterday was a pretty bad day in terms of that. So that might have contributed to the zonk. That being said, I turned screen time back on. So more grind there. But yeah, the recovery, definitely need to work on the recovery. I also realized where I'm weak. There was another thing I noticed when I'm less familiar with the problem. So I try to, when I'm working on these problems on the computer daily, I try to be like, you know, just think about what I'm doing with the problem and try to speak out loud and talk about my thought process. But there are times where I like zone in, and I've noticed it on some other problems too. I'll zone in and then I'll have to like be silent for a second as I like work through it. People probably want to know what you're thinking though. So I need to get better at that. But yeah, I'm weak on that front. I'm weak on sifting through exactly what I'm supposed to be doing sometimes because LeetCode is so straight to the point. But I guess that's the good part. LeetCode is really just a vehicle to practice like the mechanical aspects, I think, of the programming. Whereas like the actual problems that you'd get at work or something are like more abstract, and you can assemble these like atomic pieces of LeetCode knowledge into like a solution for, you know, a more complex and abstract problem. That being said, another thing I'm weak on is problem diversity. I'm doing a lot of easy problems right now, and they're kind of all over the place. I maybe have two, you know, tree problems. Both of them are centered around depth first search right now, or in order. I have a lot of random. I have like 2 or 3 random bit problems. A bunch of random different like sub problems of like array manipulation, a little bit of string manipulation, maybe just like a number. I also know some random equations like the Gauss formula. That being said, I think I just need more structured problem diversity. Maybe the solution to that is something like the LeetCode 150 or the Grind 75. So I think maybe that's the play. But I'm also going through the LeetCode list of like the top 100 interview problems. So, maybe there's something to that already where I just kind of have to get to the point and just do more problems in that list. But yeah, I'm ranting. The final point is that you might notice that I do a lot of random problems like number of 1 bits and happy number. And that's actually because I used to do daily LeetCode problems in the past. And I just recently started about like 80 days ago. 80 days ago. But technically, day 10 or 12 of what's on YouTube. But so a lot of these random problems, like number of 1 bits and happy number, I'm just relearning them so that it's easier to acquire new information in terms of like other problems. So that's kind of the goal right now. I'd like to get through learning those problems that I already learned so I could go and learn new problems. But it actually takes a little bit longer. So yes, as I'm talking now, I'm noticing that I'm definitely tired. So that being the case, I don't know if we can do an hour, and if we do an hour, we ain't doing nothing else today. So yeah, I'm just gonna jump into it. We're just gonna try and do minimum, like I said, is usually 20 minutes. 20 minutes is the goal, and I'm gonna make my text way bigger because I feel like I definitely do a poor job of making the text massive so it's readable. But on my screen, it's already big, so I'm just gonna jump into it. I'm gonna have the countdown timer as usual. I'm gonna set it for 25 minutes just to go a little further like All Might. And then I'm gonna slow down for a bit. Okay, let's just do it. Let's just get into it. So 24 minutes on the clock. We have removed duplicates from sorted array. The solution, there's no time or space complexity. I failed to add that. So function remove duplicates. I'm hoping this text is massive enough. I'm thinking it is because it's pretty big on my screen. So we have function remove duplicates. We have an array of numbers and we want to return a number. So given an integer array nums sorted in non-decreasing order, if it's not decreasing, it's ascending. So it's sorted in ascended order. Ascended order. Move the duplicates in place such that each unique element appears only once. So remove the duplicates in place. Okay, so we have an array sorted in ascending order. Then we have to remove the duplicates. Okay, each unique element appears only once. The relative order of the element should be kept the same. That actually doesn't matter, since if it's sorted in ascending order and you remove the duplicates, the relative order would still be ascending order. Since it is impossible to change the length of the array in some languages, you must instead have the result be placed in the first part of the array nums. Formally, if there are k elements after removing the duplicates, then the first k elements of nums should hold the final result. More formally, if there are k elements after removing the duplicates, so if we remove the duplicates and there are k elements remaining, that means the k elements remaining are the unique elements because we removed the duplicates. So k must be the number of distinct elements, I think. And the first k elements of num should hold the final result. It does not matter which you leave beyond the first k elements. Return k after placing the final result in the first k slots of nums. Do not allocate extra space for another array. You must do this by modifying the input array in place. So we have to modify the input array in place. Remove duplicates. And then return number of distinct elements, which would be values. So you have this array, it's sorted in ascending order. We have to remove the duplicates. So let's just make up an array here. Remove the duplicates, so we go from this to 1, 2, 3, 4, 5. And we just put 3 at the end here since we're not supposed to modify the length. Since it's impossible to change the length of the array in some languages, you must instead have the result be placed in the first part of the array, nums. Makes sense. Return k after placing the final result in the first k slots of nums. That makes sense. So we have to return 1, 2, 3, 4. So 5 after we place 5 in this last spot. So one way we could do this is with the sliding window pattern. the right side of the window is always going to be sliding towards the end, and our goal here is really to have the number of duplicates. We want to keep track of a duplicate run. So if we have an array like 1, 1, 2, 3, we want to turn this into, I'll just duplicate this line. We want to turn it something like this: 1, 2, 3, 1, 1. So the sliding window pattern, the right side of the array, which is going to be this for loop, is going to be this for loop, and we're always going to be sliding towards the right end of the array. Once you slide towards the right end of the array, what are we keeping track of on the left-hand side? The left-hand side is going to be the start of the duplicate run. So if we keep track of the duplicate run, right until the duplicate run ends, what we can do is just simply keep one element, right? So we'll keep 1, and then we'll increment our left side of the window, which we'll call LUI for last unique index. It's going to start at 0. So then our index is LUI is going to be 1, and then what we're going to do is we're going to move up forward once to keep. We have a set of duplicates. We want to keep at least one duplicate because we're deduplicating this array in linear time. We're going to copy 2 to where 1 was, and this should allow us to continue our duplicate run because the array is sorted in ascending order. So when we get to 3, well, what do? Right? Well, 2 does not equal 3, right? Because our LUI index is now at this index here, which represents 2, and our right side of the window is going to be at 3. What we're going to want to do there is just copy, like we did earlier. We're going to increment last unique index by 1. It's going to move to this 1 right here, and then we're going to copy 3 into this index, and then we should be able to return k at this point, because the number of swaps we'll have done, right? So we did 2 swaps, which means that we're not going to touch the last 2 elements in the array, which means once our right side of the window passes, I guess to return k, we could also keep a dynamic end, and then as we swap elements, our end is going to slide down. So what does that look like? That was definitely not the best explanation so far, but it's better with code. So we'll do num sub LUI, right? As soon as num sub LUI does not equal num sub I, right? We have a problem, right? Because that means our dupe run has ended. If our dupe run has ended, we want to increment LUI plus equal 1 to retain one of the duplicates. And then from here, we'll replace that second version of that number, I guess the first duplicate. So num sub LUI is going to equal num sub LUI is going to equal num sub I, since we're replacing num sub LUI. Actually, we should be safe to not have to swap anything back into num sub I. So then he'll be ignoring those values, right? And at the end, we can return LUI plus 1. So why are we returning LUI plus 1? So if we take best way to go about this is just to run the code in our heads. So we have 1, 1, 2, right? LUI equals 0, I equals 0, I is less than num's out length, right? I plus plus. So if num sub LUI, right? LUI equals 0, right? So num sub LUI is going to be 1. It's going to be this index right here. Now move my cursor. It's going to be this index right here. So if num sub LUI does not equal num sub I, or num sub I is also 0. So they're both going to equal the same number. Right, we only do something when these two aren't the same, so we're going to go to the next iteration, right? Remember, in the sliding window pattern, only the right side of the window ever slides forward. is always continually sliding forward is a better way to put it. Not always, but it's usually continually sliding forward with the for loop. It's really the left-hand side where there's room to play. And then, so if these values aren't the same, right? We started at 1, they were the same, so now we're going to go to the next index. I is going to equal 1, right? So what is num sub lui is still 0, so that equals 1. And num sub I is going to be index sub 1, which is technically the second element in the array, right? These are still the same value, so we're going to go to the next iteration. Well, now we want to see something different. Well, I is going to equal index 2. Index 2 is the last element in the array representing 2. So does num sub lui, which is 1, is it not the same? Well, is it the same as 2? Well, it's not, right? So now we're finally going to run our code. lui plus equals 1. So lui gets the value of 1. So now lui is pointing at this number here, this index in the array, and we're going to copy num sub I, which is 2, into lui. So what we get at the end is 1, 2, 1. Now, if we look, though, at lui, what we have at lui is actually just the number 1, because we only incremented it one time, right? We're actually supposed to return the number of distinct elements, because we have to, our function should return k equals 2 for this case. So we're always going to be off by 1, so we have to add 1 in this case. The secondary thing that we have to worry about, so this is return k after placing the final result in the first k slots of nums. That's a little hard to do in this case since our array is so small. So if we take a slightly larger case, something like this one, so what is it? It's 0, 0, 1, 1, right? We have 0, 0, 1, 1, right? And we're just going to start with the array as it is right now. And actually, it might be easier if we add 3, 3. So we can go through this one a little faster now, right? Because we only know we do things when the two numbers are different, right? So 0, 0. These are the same. We're not going to do anything. lui is going to point to 0 until I equals index 2, where we get to this 1. They're not going to be the same. So lui plus equals 1 gets set to this 0 right here. We copy num sub I, which is index 2, into that value. So it's going to say 1, right? So then I is going to equal to index 3. So we're at 1 again, right? And 1 does equal 1. So we're going to keep going until we get to 3. They're not going to be the same. We're going to increment lui, copy 3 into 1. So it's going to be boom. So at this point, we've already gone as far as we can, right? Because we're at this 3, and we've already swapped 2 elements. So there's no more elements to swap, right? And the way we know this, I think, is because if we do 2 swaps, so we're swapping these values, so we're not actually swapping them back into, num sub I, right? Because these values kind of always remain the same. But we know if we've done 2 swaps, and we can kind of ignore the last 2 elements, right? Because we can't shrink the array, so the elements that we swap out have to go somewhere. But since we're not actually swapping them, we're just going to know that we have 2 elements to ignore. So I think, I've never done this part of the problem before. I usually just return it like this. I think we can return if lui would be 2 in this case at this indice here. lui would be 2, and so we'd be at 0, 1, 2, 3, 4. So lui currently equals 2, I currently equals 4, and we just finished a swap. And we want to return right now. So how do we know that we're done? So we also know that the length of the array is 6 items. We have 6 items. Len equals 6. So I think we're done if the length of the array minus LUI equals I. I think that's when we're done. And the reason I'm saying that is because if we take the length of the array, which is 6, we subtract it from LUI, we get 4. And 4 is when we're actually done. All right, once we get to I equals 4, it's when we've actually done the work, right? To get the correct array. But we might be off plus or minus 1. I don't want to guess because it's important to actually know the answer to what we're doing. But I equals 4, 0, 1, 2, 0, 1, 2, 3, 4. I think we have to add 1. No, we shouldn't have to add 1. I think we don't have to add 1. I think if, like we said earlier, nums.length minus LUI equals I, then we can also return I plus 1. Oops, not I plus 1. LUI plus 1. Let's try this out. I'm not feeling very confident about this one. Oh, it works. We'll see. We have to run it on more cases. Okay, so this is wrong. This is wrong. It could also be or greater than. Because the next... Output is 0, 1, 2, 3. Right. Actually, is there a way to return? Is that actually required? Return K after placing the final result in the first K slots of nums. There's another way to do it. I think we'd actually have to I think if we, so right now we're using a for loop. I think if we use a while loop, we could potentially do this correctly. Because I forgot I was looking for, the test case I just ran failed us. So the question was, why was that? And I think it's because we're returning too soon. Give me a second, buddy, I'm almost done. 0, 0, 1, 1, 1, 2, 2, 3, 3, 4. So we're returning too early. And that makes sense. Because at this point, we would have did LU. So length 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There are 10 elements. There are 10 elements in the array. And we did 10 elements minus LUI. 10 elements minus LUI would have been 3. 10 minus 3 would have been 7, and so we should have stopped at index 7. But I'm returning this early. It also could be that I'm returning LUI plus 1 is because we're off by 1. This is kind of a guess, and I shouldn't guess, but I had a hunch. Okay, no, it's still wrong. We just have to think through it. Best way to do that is just to run the code in our head to figure out why it's failing. So 0, 0, 1, 1, 1, 2, 2, 3, 3, 4. And for some reason, my output is 0, 1, 2, 3. And the expected is 0, 1, 2, 3, 4. So LUI equals 0, I equals 0. If num sub LUI does not equal num sub I, they both start at 0, so we go to the next iteration. I equals 1, they're both the same, but we're going to check anyway just to stop skipping steps. If nums.length minus LUI, so nums.length is 10, because there's 10 elements, minus LUI, which is 0, minus LUI, which is 0, equals I. Well, I is 1, and nums.length minus LUI is 10. So that's clearly not the wave. So now we get to I equals 2. They're not the same, so num sub LUI, num sub I are not the same because 0 and 1 are not the same. LUI plus 1. So LUI plus 1 equals 1, and right now I equals 2. I equals 2 and LUI equals 1. So I equals 2, 0, 1, 2, and LUI equals 1, 0, 1. Right, and then we're going to swap num sub I into LUI. Okay, sorry, I had a brain blast for a second, but it turned out to be false. Okay, so I equals 2, LUI equals 1. I equals 2, so I equals 0, 1, 2, LUI equals 1. These are the indices, so 0 and 1 are not the same. And I'm going to duplicate this because this is going to be our input array. And this is going to be our output. So we're going to swap num sub I, which is 1, right, into LUI. And then we're going to say, hey, nums.length, which is 10, minus LUI, which is 1, is 10 minus 1, which equals 9, equal to 1? It's not, right? So then I equals 3, right? 0, 1, 2, 3, right? They're the same. We keep going. I equals 4, 0, 1, 2, 3, 4. They're still the same. I equals 5. So now, right, they don't equal the same. We're going to increment LUI, right? And then in this indice, which is 0, 1, 2, we're going to copy the different element in. So this is going to equal 2, right? And then we're going to check if nums.length, which is 10, minus I, which is 5, so 5. Nums.length, which is 10, and LUI, which is 2, does 10 minus 2, which is 8, equal I, which is 5? So does 10 minus 2, which is 8, does 8 equal 5? It does not, right? So I equals 5. 0, 1, 2, 3, 4, 5. So I now equals 6. These two values are still the same. right? So now I equals 7, right? So num sub LUI, which is index 2 is 2, right? We're going to increment that to 3, right? And then we're going to copy this 3, which is at num sub I sub 7. Right, we're going to copy this 3 into this portion right here. So then we're going to do nums.length, which is 10. 10 minus 3 equals 7. So does 7 equal 7? It does. So we return LUI plus 1, which is why our output is actually 0, 1, 2, 3. But so if we had went one more, if we had went one further, let's just say we didn't end there. Assuming this case is wrong, let's just say we didn't end there, right? I would now equal 8. So 0, 1, 2, 3, 4, 5, 6, 7, 8. We'd be at 8, and this wouldn't be legit because we're still seeing duplicates. Interesting. I'm not seeing a version of this algorithm that allows us, I'm not seeing it in my head, a version of this algorithm that allows us to return LUI. I'm not seeing a version of this algorithm in my head where we can return LUI as soon as we've placed the last element. So I think the algorithm is not going to work. I think we need something more that would like allow us to shift the end elements forward so that you don't have to go past 2 3s to get to 4. So maybe what if when we found a duplicate, we shifted it forward until there was no more duplicates? That's a lot of shifting though. And I think that's actually like n by n time. Because one shift could trigger a multitude of shifts. It's hard to know if this, I mean, I know this answer passes because I've written this algorithm before, but this specific problem, return k after placing the final result in the first k slots of nums. Return k, so we have to return k after placing the final result in the first k slots of nums. I think technically the original algorithm does that. Maybe I'm reading too closely and I literally just wasted 25 minutes. Because I'm pretty sure that's what this algorithm does. After we place the final element, without all this crazy nonsense, I mean, once you place 4 into here, I'm also not, I think the whole presumption of this, actually this makes no sense. To do what they're saying, you couldn't do it in linear time. So to return k after placing the final result in the first k slots of nums, I think is impossible. Because you have to look through the entire array anyway to know if you're placing the last one. I'm going to read the answer though. But I know this works by itself. But let's check the solution. Because I'm actually not seeing how you can return. Okay, so we just ended up wasting 25 minutes, okay, basically. Because the algorithm we're using is literally the exact same, and I got lost in the verbiage here. So we just wasted 25 minutes. But, you know, in another way, in another optimistic mindset, we actually re-verified our understanding of this problem. So I think it's actually a win-win. Feels strong, man. Wow, you know what? Now I got that. That was capped. We wasted 25 minutes. I didn't expect to spend only time on one problem, but let me see. Do I have any other problems that are close? You know, we can do more problems, except maybe I'll just speed run them. But that's bad practice. Bad practice. Speed running is bad practice because you learn to fill in gaps in your mind. Good if I was actually doing a speed. Good if I was not still learning. If I wasn't learning, but since I'm learning, speed running is bad. Zeros to the end of it while maintaining the relative order. I'll do one more, which is move zeros. So do not return anything, modify nums in place instead. We have a function which is an array of numbers, and we want to return nothing because we're modifying nums in place. So our output is going to be checked, or our output is actually being passed into the function, so our output is just going to be assessed by reference, I guess. I'll set a 5-minute timer just so I get used to working with time. Given an integer array nums, move all zeros to the end of it. So nums looks like this. And they want us to move all zeros to the end of it while maintaining the relative order of the non-zero elements. So this one is where maintaining the relative order actually matters, since the order of the elements is not sorted. So they'll actually be able to tell whether or not it was retained, the relative order was maintained. So this one is also a sliding window pattern problem. It's actually exactly like the last problem. I'm going to be honest. It's literally almost exactly the same as the last problem. Except in the last problem, we were trying to keep duplicates in our range. In this problem, we're going to keep zeros in our range. And so it's going to look very similar. So we're going to have a variable, we're just going to call it last zero index, or LZI. We set it equal to 0, and we can do let I equals 0, I is less than nums dot length, I plus plus. And so we have this input here, right? We want to get these zeros to the end, right? So our window is going to keep this array of zeros that we're constantly going to be shuffling towards the end of the array. So I'll have LZI, which is going to start at 0, and our right side of the window, which is always going to start at 0. And it's going to automatically increment forward because it's a for loop. Right? And if our current index, right, for our right side of the window does not equal a 0, then we're good, right? Just like in the last problem, the case was a little different. We were checking if two values were the same. Right now, right, the criteria for placing elements into the sliding window is the if statement, right? So an element joins the sliding window when if the index is non-zero, right, then we're going to swap it, the last 0 index, with I, and we're going to keep 0 right here in this index, right? And then whenever we find a 0, we'll just ignore it because it belongs in the range. And so since the right side of the window is constantly expanding, we're saying, hey, if you're a 0, that's great. You can come in to the window or into the group. Maybe it should be called the sliding group pattern, actually. But once we find a 3, once we find a non-zero number, right, we'll do some special swapping. So we'll have this 3, and we'll have our last 0 index, right? And then we'll swap it with 3, right? So we can do if num sub I does not equal 0, right? Then we want to do the swap like we said. So we'll keep a const temp variable, right, which is what we're going to set to num sub I. As we're saving num sub I, we're going to replace it with num sub LZI, right? And then we're going to set num sub LZI equal to temp. And so what does that look like? If we have our input here like we had earlier, we had 0, 1, 0. The first iteration, we would do nothing. The second iteration, right, 1 is not 0, so we'd swap num sub I, which is 1. You'd save that, num sub I would get the value of num sub LUI, which is 0, so this 1 would become 0, 0 would become 1. And then we probably want to increment LZI, right, because our last 0 index is now this index. So just to show what that looks like, our array looks like this, which is a shorthand version of it, right? If we say I equals 0, num sub I, which is 0, does not equal 0. I mean, yeah, it does not equal 0, and it does equal 0, right? So we're not going to do anything. We only do something when it doesn't equal 0. Dang it, I lost track of time. So it doesn't keep track of 0, and then 1. Go to the next iteration, I equals 1. Num sub I does not equal 0, so const temp. So this was our input. We're going to show our output. Const temp equals num sub I, so temp equals num sub I. Well, num sub I is 1, so temp equals 1. Num sub I gets the value of num sub LZI. Well, LZI equals 0, right? So we're going to say num sub I, right? And I'll put another variable here, I equals 1. So num sub I, sub index 1, gets the value of num sub LZI, which is index 0. So we end up putting 0 here. And since we save temp and temp equals 1, num sub LZI, I'm getting that messed up, actually equals 1, right? And so we'll have all the zeros at the end, and we have to increment LZI, right? Because if we look at LZI, which is our last 0 index, it equals 0. Well, we swapped 1 into this index, so it can't stay at 0, so we have to add 1 to it. So our last 0 index would actually be added to. And so this looks like it works. And we don't have to return anything. We ran it against a simple test case. I'm feeling confident enough to run it at least once. So that looks good, and so this should run in linear time because the number of operations we do is actually going to be bounded by the number of elements in the array with constant space. Binary tree in order traversal. You know what, actually, I don't know if I have enough in me to do one more problem. Let me see, how long have I been recording? 48 minutes. You know, I'll do one new problem, and since it'll be 12 minutes till it makes an hour, I'll set the timer for 12 minutes, and I'll try to be really conscious of time. So we have function Hamming weight, and we have n, which is a number. I actually do know a bit about this problem already. I think Hamming weight is never mind. Hamming weight, so it takes a number, we have n as a number, and we have to return a number. Right, a function that takes an unsigned integer, unsigned meaning it lacks a sign, which means it will only be positive, and returns the number of 1 bits it has, also known as the Hamming weight. Oh, so we have to count the number of 1 bits. Note that in some languages such as Java, there is no unsigned integer type. In this case, input will be given as a signed integer type. It should not affect your implementation as the integer's internal binary representation is the same, whether it is signed or unsigned. In Java, the compiler represents the signed integers using 2's complement. What is 2's complement again? It's like you flip all the bits and add 1, I think. Therefore, in example 3, the input represents the signed integer -3. Count the number of ones, it's 3. Input binary string has 3 ones. So I'm sure there's actually a way to convert this string, as a number, into binary, and then convert that string. Take this number, convert it to binary, and then convert the binary to a string. Then you could just do, if car equals 1, add 1. But I think there's a math way of doing this. And I think the string version is technically linear time with constant space. Oh, maybe not actually, because you can have a lot of numbers in a digit. I think it's linear time, or we could make it at constant time, I think. I think in JavaScript, the default type is signed, and so what we could do is I think if we default to 64 iterations, we could do if n and 1. So we're checking the far rightmost bit of n, and we'll just call ham equals 0 if n, and we could even simplify it even further. Say ham plus equal n and 1, then 1. Actually, you could just say ham plus equal n and 1, right? And it's just going to do the bitwise AND. So the bitwise AND is if we have something like 1 1 1 0 1 1, which each bit starting from the right hand side would represent 1 2 4 and 1 2 4 and 8. This would actually represent 11, I think. Because 1 would be 1, 2 would be 2, and this would be 8. So if this represents 11, we can do the bitwise AND of 1, and we'll say if 1, right, and 1. So it would look kind of like this, and 1 and 1 would be the same. So it would return 1. And then we could do n equals n, and we'll shift it 1 bit. So that 101 we saw earlier would become 101, and then 10, and then 1, and then done. But it would actually still have all zeros in it the whole time. I think this should work, but I'm curious about the underlying representation. I think in JavaScript it should be a signed integer, which should be 64 bits. And I don't think JavaScript has an unsigned integer type. It's just the number type, and I think they're all 64 bits. So I can't tell if this is 64 ones, or maybe they're all 32 bits. Let's see if we even get it right. Output was 63 and they expected 31. So maybe it's 32 bits. I'm thinking it's 30 bits, 32 bits signed. I know, I thought in JavaScript the default was 64, but it's 32 because you can tell all of these are ones except for 1, and the answer is 31. So that works. And this is kind of a bit shifting version. So that would be constant time, since we can guarantee it would always take us 32 operations to count the number of ones in a number. So the method I use actually I called a bit mask. We start with a mask m equals 1 because the binary representation of 1 is 00001. So that's what I was going for. A logical AND between any number in the mask 1 gives us the least significant bit of this number. The least significant bit is a number on the farthest right-hand side. To check the next bit, we shift the mask to the left by 1. To do that, shifting to left by 1, wait, huh? Oh, that's interesting. Okay, so the way they did it, I shifted the number itself that they gave me. They shifted the mask. So that's really interesting. If n in mass is not equal to 0, bits plus plus. That is really cool that they shifted the mask. Okay, so that's fine. We'll do happy number. We have 5 minutes. Function is happy, n colon number. We have a boolean. So we have a number, we have to return a boolean. Write an algorithm to determine if a number n is happy. Pretty cool. Happy number is a number defined by the following process. Starting with any positive integer, replace the number by the sum of the squares of its digits. Any positive integer, so we'll have 242, place the number by the sum of the squares of its digits. So 2 squared plus 4 squared plus 2 squared equals 4 plus 16 plus 4 equals 24. Repeat the process until the number equals 1, where it will stay, or it loops endlessly in a cycle which does not include 1. This sounds like a dynamic problem to me. Those numbers for which this process ends in 1 are happy. Return true if an n is a happy number and false if not. So, yeah, I think you actually can't avoid. I think this problem is dynamic, but it's not even intentional. It's unintentionally dynamic, probably, because we're saying, right, or it loops endlessly in a cycle which does not include 1, right? And how do you know if you loop endlessly in a cycle? Well, the only way you know that is if you visited a number before, right? That would mean you have visited that number before. But to know if you have visited a number before, you have to keep track of that number, I think. And so one way to do this is we could just actually use a set. And in this set, what we would do is we could have a value called n, or we'll call it cur, and we'll set it equal to n. And then we'll say this loop will run while the number isn't happy. While the number isn't happy, and so we have 2 minutes left while the number isn't happy. So to square the number, we'll call this const happy, and what we'll do is we'll take cur, we'll go to a string, and then we'll actually destructure that or spread that string into an array, and we'll map over each number in the string, and then we'll turn it into a number, and then from there we'll do a reduce function where we do a comma b, and we'll do a plus b squared, and hopefully that gives us all the numbers squared. Okay, so we have this happy number, hopefully, and once we have this happy number, what we can do is we can check if it's in the set. If set.has happy will return false. right? The number isn't happy, right? But else if, so this will be the else if, and we can actually just do one more, and we'll say if happy equals 1, then we'll return true. And I guess we could actually remove this case, because when it equals happy, it will exit, and we can just return true. I think this algorithm is fine. Oh wait, oh god, no. Otherwise, set dot add happy. I think the main problem, I don't know if this is gonna give me a plus b squared. I don't know if this is gonna give me all the sum of the squares of all the numbers. I'm not exactly certain how reduce works. I actually didn't even use cur, and happy is declared way too soon. Cannot find cur. Oh boy. So I output was false. So dot add happy. Right. So I'm thinking my function actually does not calculate happy correctly, because 19 actually should give us 0, because if you square, actually no. You square 19, if you square 1, you get 1. If you square 9, you get 18. Square 1, you get 16, and then 24, and then 4, and 8 is 16, and 20. And then if you square 2, you get 4. Square 4, you get 8. And then 8, you get 64. It's kind of tough. I just don't know if this function actually is, I don't know how reduce, I'm not that clean with reduce. Right, okay, so this makes sense. So for 7, our input, it works for the first one, but for some reason 7 gives us false. So if we take happy, turn it into a string, it's going to be 7, an array with just one element in it. And then if we do the parse int on that, we're going to get a number. And to reduce that, there's actually no b here. So if we do a squared b, maybe it's just safer to just write something smaller, a smaller function for this, rather than trying to string these together, especially when you're not in the environment you're used to. A squared plus b squared equals c squared. A squared, I mean, if there's really no b squared, because there's only one element in the array. You know, you could do it like this. A plus b squared a plus b squared you know what, I think we could make this work. We could make a squared plus b squared work. No, the number ends up being way too big. It actually doesn't make any sense. I don't get reduce. I don't get it. I don't understand how this works. I'm just gonna write a simpler version. set up a key binding real quick. So we're going to num equals just, you know, this number as a string, and then we can just do for const num of every character in this string. We actually don't have to do this spreading. I think you should be able to just iterate over this. We're just gonna do happy string plus equal, add to the end of it, parse int num squared to string. What am I writing? Oh man, my brain is actually fried. I don't even know what I'm writing anymore. I know how to make this work, but I'm just writing absolute nonsense. We're trying to calculate the happy number, which is the sum of the, it's just for a series. It's not even a series, for the sequence of elements comprising a number, we just have to square all of them. So it's for const num of happy dot toString. This would actually just be a number. Now I'm reusing variable names. We're just going to say this equals 0. And then happy num plus equal. I don't know why this is being turned into a string. So parse int of num squared if the set has the happy num we'll just call it like calc equals 0, calc plus equal this, if set has calc, set that, and then we'll say happy equals calc. So this works. I get what I'm doing, but my brain is so fried. I think I just need a break. Not from the grind, because the grind doesn't stop. But I need a break from maybe all the browsing I'm doing. I need to do better recovery. I need to get more sleep as well. But that's number of 1 bits and happy number. Yes. I think that's GG for today. My brain is absolutely fried. You can tell because I was writing absolutely anything at the end there. But I will see guys tomorrow for the grind again. Hope your grinds are going well. Mine's is not. But yes, that's day 10 or 11 or 12. I can't tell.